We'll get started. You may notice that I am probably not Nick Olson. I am Nancy. Nick couldn't do it today, so I'm sort of stepping in for this seminar. We'll sort of try to muddle through, and I hope I don't mess up too badly. Okay, so today I'm going to be going over some tips on practical study design. This is not meant to be a full treatment of the subject, but this is meant to get people who are just starting out in their research careers some things to think about when they are starting their research journey. So it's going to be a lot of information, but it's not necessarily going to cover everything very deeply. We'll touch on a number of different topics. I'm happy for you guys to stop me if you have any questions or you want me to go over something, or you can just wait to the end. In this lecture, we're going to be talking about principles of studies design. First of all, asking good research questions. What's the difference between a population and a sample? How to deal with confounding, if you can, when you're in the design process, and independence of observations. Then we might do some basic study design with, I'm going to be using R, but R is not necessarily the package that you have to stick with when you are doing your study design and your analyses. It just happens to be what most of us use. And we'll talk a little bit about sample size and randomization, and a little bit about advanced study design, although I don't know, I might talk too much to actually get to that part, but it's in here. Okay, so research itself is a process, and it's sort of iterative process. It's sort of circular, and even within these steps, it's sort of circular. You might review the literature and then identify your problem, and then review some more literature, and then refine the problem a little bit more, before you get to defining your research question. And as I am a person who does statistics, I see statistics as central to everything. That might be my own self-centeredness, but in each of these steps, statistics and quantitative methods, particularly if you are doing quantitative research, has something to contribute. In particular, this talk will be focusing on the defining your research question and the study design portions of this whole cycle. So any study really starts with a research asking, I wonder if mental health problems exacerbates juvenile delinquency. I wonder if this new drug is better than that new drug, something like that. But it's not simply enough to have that sort of wondering type of question to help guide your research process. You really need to ask a good question, and that requires that you've really identified the problem and reviewed the literature. So before you even get to defining a question, you've got some work to do. And it's really important to have a good idea of what is going on in the area in which you're researching before you can come up with a good research question. And if you have a vague research question, you likely, at the end of your study, not even going to be able to answer the question that you really want to answer. So it's important to start, before you actually design your study, with a really good research question. That's going to help you a lot. So when you are asking good questions, there are some things to think about. First of all, what is your study population? And that requires you to think about identifying that population in time. So are you doing sort of a case records audit, and what time period are those records coming from? The last 10 years, the last 25 years? Or are you doing a prospective study where you will follow people for 5 years or 10 years? You need to define that population in space. Where are you gathering your data? Where are those participants or observations coming from? You know, are they a particular subpopulation, you know, clinically, medically, or, you know, if you're an ecologist, you know, are they, you know, a particular set of birds in Blue Mountains or something like that? You need to identify what your response is. What is your outcome variable? You need to know that so you can know how to measure it well. And also, you need to know what the predictors are. What are the important variables that will be influencing your outcome? And you should also have a good idea what the hypothesized relationship is between predictors and response. So you might have this question, does social media affect people's behavior? This is not such a great question because we don't really know who is. We have peoples. So, but that's not a very specific word. So we probably need to work on who we're talking about in this research question. We have no idea what social media is. There are hundreds of different platforms, what are we defining as social media and how people are using it? That's probably something we need to be really specific about when we're trying to craft a good research question addressing this issue. We don't know what we mean by behavior. Behavior can be anything. So there are lots of things that we need to refine and to get a good research question out of this issue. Beyond that, it's just sort of a boring question. It's a yes, no. And we could probably go, yeah, sure it does, you know, but it's just not a really good question. But if you thought about it and refined it a bit, you might be really concerned about social media use amongst young people. And maybe you're focusing on the sort of algorithmic stuff that YouTube might present to people. So you go, okay, well, maybe instead of just social media affecting people's behavior, maybe I should focus on daily use of YouTube and the attention span of children under the age of 16. So now we're getting a bit of a better idea of your study population, who they are, what you are actually studying. Okay, so then we can move on to samples and population. When we conduct a study and we're collecting data, we generally are not able to access all possible members of a group. So we don't actually have access to the entire population. What we are generally doing is taking some sort of sample from that, and we draw conclusions from what we see in that sample about the population from which they're coming. So we're making inferences about a small group that we see from a small group about a larger population. So the population is the collection of all possible observations. And in statistics, where we consider the characteristics of populations, we call them parameters. So you might say something like a population mean, that's a parameter. We generally don't know what it is, but we're trying to estimate it. And our sample is what we're going to use to estimate that population parameter. And this is a collection of observations that we gathered from this bigger population. And the characteristics of the samples are called statistics, and like the sample mean. And we would use that sample mean to make inferences about the population mean. One thing to know is that, or to remember, is that in general, the sample statistics will differ from the population parameter. And if you were to take multiple samples from the same population and calculate the same statistic, all those statistics are going to be a little bit different too. And that's called sampling variability. That's sort of what statistics is really dealing with, the variability in your sample. Okay, So some characteristics about samples versus populations. Say we get a sample, I'm doing my research and I get 4 observations, and I am studying the color of circles. So I've got 4 circles, and I got 2 of them are blue and 2 of them are red. And that's all the information that I have. What I'm trying to do is take what I know from the sample and make conclusions or inferences about the population. So I've got these 4 circles, 2 of them are blue, 2 of them are red. So my best guess is that the bigger population has about 50% blue and 50% red. So I think it probably looks like this, and that's based on what I see in my sample. But it could be that my sample is just a little bit quirky, and I got 2 blues and 2 reds, but my population looks like this. Mostly red, just a few blue. And it just happened that I got a sample that has 50% red and 50% blue. Yes?
So for example, if you have a cohort, could be either a sample or a population?
A cohort, you mean like you're doing a cohort study?
Yeah.
Generally, that is, you're using the cohort as a sample to make inferences about a larger population in general. So, like if you were doing a study on I don't know, smoking or something, you're not going to be able to access every single smoker in Australia, but you may be able to get a bunch, observe a bunch of people in New South Wales, so that you might make inferences about Australian smokers in general. There are questions about whether that is a good representation of smokers in general across Australia. So you could have a situation like this. And that's one of the things that we'll be talking about a little bit, and about how your sample and your research design can be threatened if you're not thinking about those types of things. Yeah. Mm-hmm. So in this situation, I've got my 4 observations, and it's actually not a very good representation of what's going on, but I don't really know that, but this is the best guess that I have. Say instead I had a slightly larger sample. I have 8 circles, and my 8 circles are, again, 50% blue, 50% red, once again, I could have a population where I actually have, much more red than blue, but it's less likely that my larger sample of 8 is going to end up with 50-50 if the population actually looks like this. So this is sort of demonstrating that with a larger sample, you're going to get a better and better idea of what is actually happening in the population. I mean, it's not impossible for a larger sample to look like this when the population looks like this, but it's a lot less likely than when you've got a smaller sample of only 4 circles. So the idea here is that a sample is going to differ from what's actually going on in the population, but with larger samples, you tend to get closer to a closer picture of what's going on. When we are designing our quantitative research studies, there are generally 2 types of studies that people are looking to conduct. We have experimental studies and observational studies. Experimental studies are studies in which the researcher introduces some sort of intervention and then studies the effects. There's some sort of manipulation going of the conditions that is occurring. It could be that you end up with 2 groups, and one group gets one particular intervention, the other group gets a different intervention, or it could be one group that gets all interventions at different time points. Observational studies, these are studies in which researchers observe the effect of a risk factor or some sort of diagnostic test or other intervention without trying to change who is and who is not exposed to it. So there isn't some sort of researcher manipulation going on. Now, a very important issue when you are designing your research studies is confounding. And confounding means that when there are differences due to experimental treatments or predictors that cannot be separated from other factors that may be causing the observed differences. And so, for example, you are a developmental researcher and you measure children's heights and their mass abilities, and you find that children who are taller also tend to get higher math scores on some tests that you give them. And you're like, wow, this is really groundbreaking research. Somebody might go have a question here or have some idea about something else that might be happening. And so what would that be? What's that? Yep, that's with the one thing. Mm-hmm. Yep. Oh, that's yep.
And they might want the climbing next to it, and they will have better math.
But yes, yeah, that's a really good inference. Yep.
If you just want to make it simple, if it's the only thing you're measuring in height, it would just be age.
Absolutely. Yep. Yep.
They're older.
Yep. Yeah, if they're older, they might have more exposure to math. If they're coming from better SES, they might have better nutrition and access to education. So, yep, those are two really good things. Yeah. So, like, if you were this researcher, you probably should have thought of these things before you started, your study. Because those are absolutely some things that could confound the relationship between height and math ability. So to remove the effects of confounding, you do have some options. You can conduct experiments, and a well-designed experiment can remove effects of confounding. And you can actually show some causation with a well-designed experimental study, so that you might be able to show that your intervention does actually increase math scores or something like that. In observational studies, you can do some statistical control for confounding variables, but you really need to know your subject area really, really well, because you have to measure it. You can't control for it in your statistical model if you do not have the data that you need. So you have to think very hard about what could be a confounding variable and the relationships amongst those possible confounders and your exposure and outcomes, and construct a statistical model really well. It's hard. It's hard to remove the effects of confounding in observational studies. So if you are doing an observational study, it's really important for you to talk with other people who have lots of experience doing this, and lots of people who have really good substantive understanding of the area in which you're doing your research. Okay, so let's talk a little bit about some manipulative experiments, things to think about. To conduct a successful manipulative experiment, you need controls, replication, and randomization. These are some things that are really important for a successful experiment. So what are controls? Controls are sort of the group that will give us an estimate of the counterfactual. So what would have happened if the people in the treatment group had not been treated? That's sort of what we're trying to get at with our controls. Replication. Replication here in the study design context, we're not talking about replicating previous test results or previous study results. We're talking about replication in your data. This is so, when I say replication, I mean we need multiple observations of the thing that you're trying to study. And we need that because we need to be able to attribute any differences between your treatment and control to the intervention rather than to innate differences of the things that you're studying. So if you only have like, one observation in each group, you don't know if it's because, the treatment happened to this person or this person just happens to be like really good at math. Yeah. And randomization. So when you're doing a manipulative experiment, you randomize, people or sites or order of presentation of things, and it overcomes confounding when measuring that treatment effect, because regardless of the confounders, the probability of being in the treatment group or the control group is equal for all participants. You're not going to, in general, have any association of any confounder with being in the control or the treatment group. So it breaks that relationship there. A little bit more about controls. In an experiment, it's the treatment group that does not receive the intervention of interest. For example, if you were an ecologist and you're studying how predation affects behavior and hormone levels of a particular prey animal, the researcher may exclude predators from some areas and not others. And in this situation, you have some areas with normal predation. There's no intervention there. You're not doing anything. You're just observing what's happening. But the other areas where you're removing the predators, that is some sort of intervention. So you have predation removed, and that's your intervention group. But a control group or control condition does not necessarily mean there is no treatment. So it's not simply we don't do anything or they receive nothing. There are situations in which it's unethical to provide no treatment at all, particularly in medical or psychological behavioral research. A control group could be a group that receives conventional treatment or what's the current standard of care, rather than no care at all. That would just be unethical in terms of health outcomes. So, a study in which a researcher is examining the effect of a new drug is not necessarily a new drug group versus no drug group. It could be new drug group versus conventional drug, or even if the control group really isn't getting anything and they're really sort of looking at maybe adverse effects of a new drug, the other group could get a sugar pill so that they're getting something, but it's not anything that is metabolically or biologically active. And that happens because it's been observed, particularly that people, when they are included in research studies, even if they're not getting anything, they may improve. They may look a little like the intervention group just by being included in a study like this. So you need to remove the effect of being included in a research study, and also but you can do that by giving them some sort of sham treatment or sugar pill type of thing. Controls that you have in your study, or should look as close as possible to those in your treatment effect or your treatment groups, and hopefully your randomization really does take care of that for you. Replication. Okay, so you are a researcher in biology. You guys are like across all research areas in this class. But now you're working on your biology stuff, and you're doing some basic science and using mouse models. You know that you need replication. So and you're also really conscious of using resources. So you might want to design a study where you take multiple measures from one mouse in group A, multiple measures from one mouse in group B. I've got replication. I've got 3 measures in each of them. I'm going to analyze my data and find a difference between treatment A and treatment B. This is actually a really bad idea because you have replication within a mouse, but you don't have replication at the mouse level. So you're getting a really good idea of what's going on in mouse A, in that top panel, and in that mouse in group B. You've got a really good idea of whatever it is that you're measuring, but you still can't attribute anything to an intervention effect because it could just be that these 2 mice are different in some way. So when you are planning your study, you need to make sure you have replication at the correct level in order to make a good inference about any treatment or intervention effect. So it's a better idea to do the study in the bottom panel there, where you get 1 measurement per mouse, but you have 3 mice in each group. So that's getting replication at the mouse level, where we get a better idea of about the intervention working as a group rather than confounding that with the mouse itself. Okay. Any questions on some basic things on experimental studies? Okay. So some things to think about for observational studies. If experimental studies are so great at showing causal relationships, why would we even consider observational studies? We already have a method that that will help us, establish causality between some sort of exposure and an outcome. Well, sometimes observational studies are the only way to get that sort of evidence. Due to ethical reasons, we can't take a group of people and randomize them to be smokers versus not smokers. We can't do that. It's unethical. Maybe an experiment would be really, really, really expensive. And we just do not have the money and the resources to do that and run that type of study. And so the only way that we can get some idea of what might be going on is to use existing databases and do it that way. Another situation in which observational studies are helpful is when you have really rare outcomes. So a lot of times with really rare medical conditions, we can't really study them except using observational data because there just isn't enough people out there for us to run an experiment. And even if none of these things are the case in your situation, observational studies are a really good way to help generate hypotheses that you might be able to test later on with manipulative experiments. So even if it's like not the last thing, they're still worthwhile to consider an observational study. Now there are lots and lots and lots of different types of observational studies, and I'm not going to go over all of them, but I will mention a few that are very common. So first of all is a cross-sectional study. This is like a quick snapshot of exposures and outcomes. And it can be fast and cheap, and it's really good for saying, yes, we do see that there's a relationship here. There's some sort of association going on. And so maybe it can be used to help you identify things that are interesting to investigate further in other studies. The thing is, because you just get one quick picture of what's going on, it has a lot of problems with bias. So you're not able to determine if your sample is really representative. Oftentimes, you may not be able to measure all the confounding factors that you really need to. So there are lots of problems in terms of identifying causal relationships. This is not the type of study that can help you do that, but it can help you identify things that are interesting and worth looking at more deeply. Case control, this is a retrospective observational study where you're sort of starting out at the end. You're starting out defining your samples based on the outcome. So this is really popular in public health and medical research, where you choose your sample based on cases, which are people who have a particular diagnosis or medical condition or some sort of surgical procedure, and those who do not have that outcome. And then you can look back and in their history. It could be medical history, demographics, all of those types of things, and see associations with their exposures and whether they are a case control. These are really good for rare outcomes because if you were to just randomly select a bunch of records, you may find that you may be interested in a particular rare outcome, but you don't see it very often. So you can start with identifying your 50 cases because you know that that's all there are in New South Wales or something, and then identify some controls to go along with them and then examine their case histories retrospectively. So it's good for rare outcomes because you get all of the information that you need, but it's bad for rare exposures. So think about that if your research question is focusing on a rare outcome or a rare exposure. The drawbacks, again, you may have bias problems and you may not get all of the information about the exposures that you're interested in, unfortunately. And it can also be really difficult to identify good controls to include in your study. That's when you're doing these types of studies, that people spend a lot of time figuring out who the controls should be and finding them. That's very important. And another very popular type of observational study is a prospective cohort study. There's also retrospective cohort studies, but focus on the prospective cohort. So these are the types of things where you gather sort of a bunch of people and you might follow them for over time. So you might have people with the exposure and without the exposure, and just follow them over time to see if they get the particular outcome that you're looking for. So these might be smokers and non-smokers, and do they, develop emphysema in 10 years or 20 years or something like that. These types of studies do lend themselves to having the best evidence for inference and associations between exposures and outcomes. You can also estimate time-based associations between exposure and outcome, which is something that you can't do with the cross-sectional study that I mentioned first. They are expensive and they take a really long time. Those are some two big drawbacks. You need to have lots of people involved, lots of resources involved to continue observing these people and getting the data that you need over a long period of time. And of course, when you are studying things over a long period of time, particularly if your subjects are people, you lose a lot. There's a lot of attrition, a lot of loss to follow-up, and a lot of changes in exposures. So if you are studying those people who are smokers versus non-smokers, there are lots of people who will become non-smokers, but they started out as smokers, and some people who will become smokers who started out as non-smokers. There's lots of things that you cannot control in these prospective studies that does make it difficult to really pin down any strong relationship between your exposures and outcomes. And like I said, there are a lot of different kinds of observational studies, and so this is not exhaustive. Yeah. Okay, so some general difficulties when you are running these types of studies, these observational studies. Confounding, obviously, is the number one thing that you need to think about, and controlling for confounding is really hard. It's just really difficult. There are lots of things to think about, lots of different relationships to take account in your planning of your statistical model. You can have difficulty in defining like who are exposed and who are not exposed, depending on what you are actually studying. And when you do this, if you're not really careful and think very hard and consult with lots of people who are very smart in your substantive area, you can actually induce bias rather than remove it. So one of the things that can help you when you are planning these types of studies and planning your statistical model are what's called directed acyclic graphs, DAGs. And these are tools that help visualize how variables are interacting with each other and causing confounding or breaking confounding, or things that you don't even need to worry about. So if you are doing observational studies, I highly recommend you get a little bit of knowledge about directed acyclic graphs and sit down with those before you've really collected your data, and definitely before you do any analyses. And there are some nice online DAG generators that you can play around with that can help you determine whether a particular variable does need to be adjusted for statistically as a confounder or not. Okay, so for example, if you are a researcher looking at smoking and lung cancer, you may be using some observational data from a longitudinal study. We've got different follow-up times for different people. So there are a few things that you need to really think about, and they're actually kind of hard to do. So how do you sort your patients into smoking and non-smoking groups? So is somebody who smoked for 10 years before being included in the study, are they a smoker or a non-smoker? Is somebody who smokes a couple cigarettes every 6 months or so with their friends, are they a smoker or are they not a smoker? Are people who quit smoking, are they smokers or non-smokers? So these are things that you really need to figure out before you can really do a really good analysis on your observational data. Stuff like this also, often when we're talking about exposures, we're able to say, okay, this is the exposure if they got COVID in 2020. But for a data set like this, that time zero can be really difficult to determine or define. These are some things that you might run into when you are designing your observational studies. But that does not mean you can't do a really good observational study. And you can do that by following sort of the guidelines in target trial emulation. Okay, so what is a target trial emulation? So imagine a well-designed clinical trial. That is going to be your target trial. So you're sort of coming up with a hypothetical situation in which you were able to run some sort of clinical trial. That's sort of what you're aiming for. It doesn't have to be ideal, particularly because you're going to design it knowing what your available observational data look like. So you have a set of observational data, and you know that you want to study a particular association. So how would you, if you were going to be able to design a trial, design that trial in a really good, robust way, given the information that you know you can access in your data set? So that's why I say it doesn't have to be ideal, because an ideal trial might have things and characteristics and variables that you don't even have access to. So there's no point in designing a target trial that you would never be able to emulate in the first place. So it just needs to be a well-designed trial that is relevant to the observed data that you actually have. You could then create a detailed written protocol for that hypothetical target trial, including things like the eligibility criteria for being included, treatment strategies, allocation of procedures, what the follow-up period is, you're obviously defining your outcome, and writing up a statistical analysis plan. So it's like you're actually designing the trial, but you're not actually going to run that trial because you can't. You're just going to try to emulate it. And the emulation part comes in through mapping each of these concepts that you included in your protocol to the observational data that you have. And of course, in these processes, when you're actually going through them, there will be deviations from the protocols that you've written up, and you need to document those. But what happens when you do this is that you are getting almost as close as possible as you can to being able to make a causal inference about a particular exposure and a particular outcome with observational data. And so you can do a really, really good observational study, or study, to observe some sort of exposure and its relationship to an outcome with observational data if you're doing these target trial emulations. And if you are interested in this type of research, Hernan and Robbins in 2016 have done a really good job of talking about what the idea is here and how to go about doing it. Also, the talk after this one by Kristen Hunter, this target trial emulation is included in the world of causal inference. And she's going to be talking about causal inference and saying way more smart things about it than I know. So I encourage you to stick around for her talk if this is something that you're interested in. It should be really good. Okay, are there any questions on sort of experimental designs or observational designs before I move on? Yes?
The third part of the target trial emulation.
Yeah.
So I must have missed the link of the third to the second part of the third from the link of the target trial emulation.
Oh, it's just saying like, yeah, or like in any research study, and it particularly happens in clinical trials, things happen that don't go according to plan. You have to make some adjustments sometimes, and the same thing will happen here. Maybe you thought that you had a really good measure of socioeconomic status, and that was an important part of the target trial. But it turns out that you don't have that access to that information. So you need to sort of adjust how you are treating that variable. Yep.
So in the case of the emulation, are you writing your protocol of the emulation, and then still within the emulation, you're then documenting
Yes.
how that protocol deviates
Yeah.
from,
Yep.
Based on what
Yeah.
your actual observations were?
Yep. Mm-hmm. Okay, so now we're going to move on to actually getting down to some nitty-gritty on your actual study design rather than thinking about things. We've done all the thinking, maybe not all of it, Now we're going to actually do some stuff. So we've defined a really good and really interesting research question, which is going to add new and novel knowledge to our substantive area. We've decided on the type of study that we want to do. Now we need to focus on some details. And Mariah is reminding us that we need to focus on effect size, sample size, and power. And we might need to do deal with randomization, particularly if we're doing a manipulative experiment. So, effect size. Okay, what is effect size? So often when we're getting ready to, when we're planning our study, we're interested in like how many mice do I need? How many schools do I need to go into? How many participants do I need? And so we're planning on sample size and stuff, but we can't do that until we know what our effect size is. And our effect size is the magnitude of the effect that we're hoping to detect in our study. Remember that we don't really know what's going on in the population, but an effect size is something that if it existed in our population and is reflected in our sample, is interesting and meaningful, and is like something that's really neat to find out. And we also have to be a little bit practical. It's got to be an achievable effect size. There is no point in planning a study where the effect size you would never see. You would never see an intervention increase somebody's math score by 50% on average, or 50 points on average. It's really got to be something that is interesting and really neat, and that you would actually achieve. So we can determine these things, first of all, based on our knowledge of the substantive area. We are, experts in the thing, area that we're studying. Obviously, there's some information lacking, but we have a really good handle on, what you typically see in this substantive area. So the first thing to rely on is your own knowledge and those of your research team. And then we can also look to previous literature that has been published in order to get an idea of what an achievable, feasible effect size is. And then the clinically meaningful or interesting question is a little bit separate from that. So, for example, we may not care if treatment and control groups only differ by about 5% on our outcome. That's not all that interesting. But we may be interested if we found a difference of 10%. That might be a really worthwhile thing. So the effect size we might use in some sort of sample size or power calculation is 10%. So if we are able to see a 10% difference between our treatment group and our control group, that would be really great. So how many people would I need to recruit in order to achieve that? Okay. So how do we go about calculating power and sample size? So the aim of a study is to detect an effect in your sample if one is actually present in the population. And if you fail to do that, that's what we call a type 2 error. And you might also think of it as sort of a false negative. You're missing something that's actually there. And when you are planning your study, one of the things that you can do to minimize that probability is get a good sample size estimate, or a large enough sample size to detect it. And the sort of opposite of that type of error is what we call power. So when you maximize power, you minimize that false negative type 2 error. And it is the probability of detecting the effect you specify, or one that is larger, given that that effect actually exists in the population that you can't observe. And there is no point in running an experiment or a study if you have very little probability of detecting that effect. So you might have a really great research question, but if you do not design your study well, or you don't recruit enough people, your power is going to be very low. You'll have a very low probability of detecting an effect that actually does exist. So you will have wasted lots of time and resources, and you don't want to do that. So important things to have ready when you are doing a sample size calculation before you run your experiment. A good idea of what your effect size is. What is it that is interesting, what size is interesting and feasible. You need an estimate of variability of your outcome in the population. You need to know how your data will be generated and what statistical model you intend to use to analyze your data. These are all really important in order to get a good sample size estimate when you're planning for your study. When you are doing this, you have lots of tools available to you to do it, and not all of them are proprietary software. You can get G-Power, which is free. You can download it, and it's got lots of different research situations, and you can generate a sample size calculation that way. It's relatively basic, so it has lots of really common statistical models that you can get sample size calculations for, but if you get any level of complexity in your research design, it's not going to be the one that you need to use. PASS, which is Power and Sample Size, is a software package. You can get a free trial, and it is really good. It's got lots of different situations that you can use, and ones that can be quite complicated. It's really a fantastic program, but once your free trial's over, it's really expensive. So, but it's really good. And then software packages typically have some facility or modules in them to do sample size and power calculations. So like SPSS for a really long time, if any of you are using SPSS, for a very long time it didn't have it at all. And in recent versions, you can do some basic sample size calculations in it. But SAS and Stata and R all have some really nice packages and modules with them. And we're going to be doing a little bit in R. And R is free, which is really great. It does require a little bit of a practice in getting to use it if you are not an R user. But it's probably got the most comprehensive set of packages built for power and sample size calculation. And for lots and lots and lots of different research areas and statistical models. So we're going to talk about a t-test. Let's consider an experiment with 2 treatments. So you're looking at, apparently we really like to study math scores here, maths exam, and you want to see if it's better for students to study the night before or rest. So you want to a sample of people, and some of them you're going to have do a bunch of studying before the exam. Some of them they're going to probably study before and then rest the night before, and then you're going to have them take their exam and then take a look at scores. So the responses students mark on the exam, and you're interested in detecting a difference of 4 points. So that is a meaningful difference on the scale of the scores from the math test. And you know that from previous exams, the standard deviation of exam marks is 7. And you also know that students in a particular school tend to show a correlation of math scores of about 0.6. So you have a little bit of information about the relationships amongst the students in a particular school. You are planning on randomly selecting Year 10 students from across Australia and allocating them to study or rest before their exam. So what sample size do we need in order to detect my difference of 4 points in this study? Okay, so like I said, you need some information to get that ready before you actually do your sample size calculation. So a couple of things that are sort of standard for these types of things are the type 1 error rate. So the type 1 error rate is the probability of finding an effect in your sample when one doesn't actually exist in the population. And we typically set that at 0.05. It's often called our alpha level. And we can choose our level of power. So at a minimum, it's people, you expect power to be 80%. But if you're doing, particularly if you're doing a grant proposal and you're doing a sample size calculation, 90% is standard. So that type 2 error, you're keeping pretty low at 10% or so when you have 90% power. And we have our effect size estimate, which is 4 points. That's our meaningful and interesting difference. And variability estimate, we know that it's about 7 or so. So if we were doing this in R, I want to be able to detect a mean difference of 4 points between two groups at 90% power, alpha of 0.05, and apparently it's 10, not 7. So okay, so with an effect size of 4 and a sigma of 10, I forgot to change it on the earlier slide. Apologies about that. And we can use our power library and say, hey, give me power. I am going to be using a t-test to test for a difference at the end of this study between the means of those two groups. And I have my effect size. I am scaling it by the standard deviation. And there's my power level is 0.9 and my significance level of 0.05. How many people do I need? And so this one says I'm going to need about 133 people in each group. So 266 students randomly selected from schools, Year 10 students from across Australia for this study to achieve 90% power. Okay, that's a lot. I don't know if I have enough time and resources to select 266 students and do this. I don't know what I'm going to do. Well, first of all, I'm going to show you that SPSS gives you the exact same thing. So you can do this relatively simple sample size calculation in SPSS as well, and you can see that it gives you the same sample size estimate as the R procedure did. Okay, so like I said, I don't know that I can get 266 people. I don't have the time, I don't have the resources. Maybe I need to rethink what I'm doing. And one of the things that I can do is think about my research design. See, I was going to randomly select a person, 266 people, and then allocate 133 to one group, 133 to another. But maybe I can rethink that. And maybe that will change how many people I need to recruit. So instead of randomly sampling 266 Year 10 students, we could randomly select pairs of students from schools and assign one of the students to study the night before and one of the students to rest the night before. And because we do know that there is a correlation of math scores within schools of 0.0 or 0.6. So what we would do is select pairs and then randomly allocate within a pair. And then we can do a t-test at the end and test for a difference. This is an example of what's called blocking. And in this situation, each school is a block, or each pair is a block. And we are randomly allocating each of the members of a block to one of the two treatments. And what happens when we do this is that we can increase our power by doing this, assuming there is a positive correlation amongst the members of that block. And we do know that the correlation amongst math scores of students within a school is positive 0.6. So we can capitalize on the fact that we know that there is that correlation by doing, changing our research design just a little bit. And so here's what happens when because I thought about it, I don't think I can get 266 people. So if I change it and I capitalize on the fact that there's some correlation here, now, because we got some dependency between the scores from each school, from each pair of students, our standard deviation is no longer 10, but it's adjusted by the fact that we have some positive correlation here, and the standard deviation is now down to 8.9. So when we have less variability, we increase our power. And we can see that we only need about 55 pairs, so about 110 students in total, in order to get the same level of power for the same difference in our test scores. I can do 110. I can find 55 schools to let me come in and do this. I couldn't do almost 300. So it's a nice demonstration that if you really think well about your study design, you can increase your power quite significantly if this is a situation that is available to you. And again, just showing that you can get the same calculation from SPSS. So if you are a researcher in lots of different areas, blocking in this kind of way in your research design can be really helpful. So for example, if you're an ecologist and you're studying trees, you can consider each tree a block and maybe choose 10 leaves on each tree, and 5 of them get one treatment and 5 of them get another. So obviously leaves on a tree are related, so you would be able to increase your power that way. If you are a person who works in a lab and you're doing some samples in a centrifuge, each run of a centrifuge can be considered a block, and it would be good for you to have some samples from each of your treatments in each run of your centrifuge. So you can consider it that a block as well. A person can be a block. So you can put your 2 treatments in one person. So like I work a lot with people in optometry, and they'll do studies where they have a lens in the right eye and a different lens in the left eye, and then they'll run measure their outcomes. So an individual can be a block as well if you're putting the 2 treatments within the person or the mouse. So things to think about when you are calculating your power or sample size. First of all, I gave you a couple of pretty straightforward examples, but in general, actually calculations can be really difficult and hard to do. Like with any degree of complexity, automatically the difficulty is like it goes up so quickly. You may find that there's not a lot of research into the thing that you're trying to study, and so you can't rely on what has been shown in previous research as an interesting or feasible effect. And also that goes along with often not even knowing what a good estimate of variability is. And so you might get stuck there. What are you supposed to do then? There are a few things that you can do. One of them is, you can run a pilot study, to get some sort of idea of an effect size and some variability. Like I mentioned, if there is any bit of complication in your study design, often the sample size packages will not be able to accommodate that. These tools that are available to you may not even work for you. Or if you are planning on using a non-standard model for your analysis, these packages often don't accommodate those either. So you can't get a good sample size from those tools. So if you have any bit of complexity or any questions at all when you are planning your study, it's good to talk to somebody who does these things and can help you out with that. Now, another thing about sample size and power calculations, we're usually doing it to calculate a sample size. What is a sample size to detect this effect? But you don't have to restrict yourself to calculating a sample size. Sometimes you already know what your maximum sample size is. And this often happens in basic research when you're like, I only have access to 50 mice. What can I do with 50 mice? And so you can sort of start at the end, basically. It's like you're starting with sample size. What level of power would I have to detect my effect size? Or what effect size would I be able to detect with 90% power? So you don't have to restrict yourself only to calculating sample size. You can actually calculate power or the effect size that would be detectable with your given sample size. And if you are or foresee in your future some sample size calculations coming up, we do have a short course next week, actually, by Mark Donahoe, who is with the Clinical Research Unit. He does a full-day short course on sample size calculations, and that's happening May 27th. So if you are interested, you can check out our website and see if it's something that you might want to sign up for. Are there any questions on sample size and power? Yes. If there is some way that you can define related groups in there, yeah, that could probably work. What it would mean is that it would increase your power estimate, or it would make it so that the effect size that you are able to detect is pretty small, and that's that helps you as well. Okay, so it is 10 after 11, so I'm obviously not going to be able to get through everything, I think, but we'll see what we can do with the rest of the stuff. Okay, so one of the things that's really important in designing your studies is knowing the level at which independence exists in your data. Like in that sample size calculation thing that we just did in the first situation, independence occurred at the student level because I was randomly choosing 266 students. So knowing one thing about one student gave me no information about any other student. But in the second situation, independence occurred at the paired level. So knowing what was going on in one pair gave me no information about what was going on in another pair. But within a pair, we knew that there was likely to be a correlation between those math things. So when you're doing these things, knowing the level at which independence exists is really important. So for example, if you are an ecologist and you are studying fish or something, and you've got aquariums, the fish in one particular aquarium are more like each other because they're living in the same environment than they are to a fish from another aquarium. So they're exposed to the same conditions, whereas the other aquariums can be quite different. Measurements in the same person are more similar than measurements from different people. And in space, measurements taken close together, or even in time, measurements that are soon after one another rather than more separated in time are more similar. So those are some examples of where dependence exists in your data. And that must be taken into account in your experimental design and your analysis. So you really need to know how your data, where that independence does lie. And if there is dependence, you need to make sure that you are accommodating that in your study design and in your analysis. So if you are doing experimental designs, you can ensure independence by doing random allocation. You just need to know at what level you're doing it. Are you doing it at the student level or the pairs of student level? And by random sampling for either the students or the pairs of students for manipulative experiments and observational studies can help ensure independence. You wouldn't want to get multiple pairs of math students from the same school because they're going to be much more related to each other than they are to be another pair. So you really need to make sure that that the pairs are coming from different schools, unless you're able to adjust for the school as well. Now for random allocation, there are lots of different sort of schemes in order to do that. And the simplest one is sort of a coin flip. So if you've got two interventions that you're comparing, you might know that you're going to have 20 people. So you can flip a coin 20 times, and the first person comes in, you're a red person. The second person that comes in, you're a blue person. And it's really simple. But the thing is, when you do a randomization like this, you are not guaranteed to actually have equal or similarly sized groups just because of random chance when you are flipping that coin. So this is not the best way, particularly for small studies, because that's where it shows up really most, that imbalance can happen. So it's easy, but it's not particularly good. You can also do something called stratified random allocation. So you may have an idea that you, like older people and younger people, you want to make sure that they're balanced in your treatment groups or intervention groups. So you know that if somebody is younger than 45 years old, we're going to call those people our younger group. People who are 45 years and older, they're going to be our older group. And then within those groups, I'm going to do some random allocation. And in that way, you're making sure that your two treatment groups have a nice balance of older and younger participants. And that's one way to sort of get away from age being a confounder in the relationship between your intervention and outcome. So that's really good. It can be relatively easy if you've got only a few groups that you really want to stratify on. Once you go like, okay, we need age, we need sex, we need level of education, and so we're going to stratify on these things, but you have to do all combinations of all of those. And that's a lot of strata to populate, basically. And it can be very difficult to design a study when you've got more than a couple of these strata that you're trying to control for. And it does require you to really know who your people are going to be, and you may not necessarily know that. Okay, so I am going to bring in the word blocking again. And this is sort of a little bit of a different connotation of blocking, and I'm sorry that it's the same word in a different context. This is sort of a different thing, but is an important one to mention. And my image got cut off there, but pretend you can see it. Okay, so this is a really good way to do randomization when you're really concerned about getting about equal sample sizes in your groups. Rather than coin flipping and getting a list of your random allocations for your entire sample, what you do is sort of break it down into blocks of a particular number of people, and within that block you can randomize your people into your reds and blues. So what you can do is sort of construct all the different possible combinations for, say, 4 or 6 or 8 people being randomized in your study, and then you randomly permute those possible combinations to come up with a randomization schedule. The really cool thing about this is that you don't have to restrict yourself to only 4 people in each block. It can be, so I've got 2 treatment groups. I could use blocks of 4, 6, and 8, and that's really good if you want to disguise from the researchers in particular what the next person's allocation is going to be. So if I'm a researcher and I get to that 4th person, when I do it like this, I know that the first person was a blue, the second person was a red, third person was a red. So that means that the 4th person has to be a blue because there's equal allocation in my blocks of 4. But if I have different block sizes, I don't know if that 4th person is the 4th person in a block, or it could be the 4th person in a block of 6. And so it's really disguised from the people who are implementing the intervention if they have any previous knowledge of what had happened before. So this is a really nice way to do some randomization if you're really concerned about having equal blocking sizes and disguising people's allocation to the people running the study. Okay, I think this is probably the last thing that I'll talk about because we're sort of at the end. So you can do these randomization schedules in lots of different packages. There are a bunch of tools out there that are free for you to use. So there, if you want to do some simple randomization or some relatively non-complicated randomizations, you can use a website. There are a bunch of different facilities and statistical packages that you can use as well. But also remember that it may be really important for you to get somebody else to do it for you. Particularly if you're doing clinical trials, people who are doing the research team should have no contact with the people who generate the randomization schedules. They do not want any contamination, any knowledge of what is actually happening to the subjects in terms of allocation to come back to the people who are responsible for the data and for the data analysis. So you may need to engage a completely independent person to generate your randomization schedule for you and provide it to, I don't know, a person who's running a red cap in order to implement it, to secure everybody from any implication of bias and knowing allocation status. I think I'm going to stop now because it's already 20 after 11. I am happy to answer any questions or comments. Yes.
So these days they're talking about the real world evidence, real world data.
Real world data. Mm-hmm.
Clinical trials especially. So in your wisdom, do you think the RCT, which was the gold standard, is going to be affected by that? Like and qualitatively, if you can, like how and why and
So it's going to be affected by what?
the real world evidence and real world studies.
Ah.
To use this synthetic data.
Oh,
This one.
I don't know that I wouldn't think that holding up RCTs is as sort of the standard of evidence is going to change. I think that will remain as sort of what everybody wants to use as the best evidence for a a relationship or an intervention. Those types of things maybe might point to other types of interventions that are important, but I think that the RCTs are still going to be maintained as the gold standard. Any other questions? Yes?
So you mentioned before that there was like a trick to calculate the confounding variable.
DAGs, directed acyclic graphs. Yes.
Okay.
Yes. Yeah, I should have put that on the slide. Yeah, but directed acyclic, so ACYCLIC graphs. There is a website called, people will call them DAGs, D-A-G, but there is a website called Daggitty, D-A-G-G-I-T-T-Y, that you can do and play around with them online. Like you can make pictures and it'll tell you, you've got a confounder here. Yeah, so they're very helpful. Yeah.